Module 9, Lecture A, Saving Models. By the end of this lecture, you will be able to export TensorFlow 2.20.0 models using the saved model format with appropriate signatures, use Keras model.save and save weights APIs to manage checkpoints and full model exports, and verify that saved models can be reloaded and produce consistent predictions. TensorFlow SavedModel Essentials. Saved model folder structure. When you export a model using TensorFlow's saved model format, it creates a structured directory instead of a single file, which is important for deployment. At the top level is a folder you name, and inside it are subfolders for different model versions, such as version 1, 2, or 3. Each version folder is a complete snapshot of the model, including its parameters, computation graph, and metadata. This structure makes the model portable and language independent, so you can move it between machines or teams without the original training setup, as long as the TensorFlow runtime is compatible. Each versioned folder of a saved model is organized so different system components can access what they need. The main export is a protocol buffer file called SavedModel, which stores the computation graph, serving signatures, and metadata such as usage tags. Alongside this, a variables directory holds the numerical weights and tensors split into index and data files for efficient loading. By separating the model structure from its parameters, you can inspect or modify how the model is built without loading all the weights, which is especially important for managing large models in production. A saved model directory can include not only the model's computation and parameters, but also extra assets needed during inference, which helps avoid deployment problems. For example, a text classification model may store its vocabulary or label mapping so that preprocessing stays consistent from training to serving. Custom layers can also save lookup tables or transformation specifications, allowing the serving system to reconstruct the full pipeline from input to output. In this way, a saved model acts as a complete, portable package that is ready to run across different platforms and languages. Python code, saved model, folder structure. This script demonstrates how TensorFlow saved model folders are organized. It first builds a very small example model and saves it in the saved model format. After saving, it examines the contents and structure of the saved model directory. The goal is to help you understand what is stored in a saved model and how its files are arranged. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. It is commonly used in notebook environments to make sure that this exact version is available. Doing this helps ensure that the code that follows, which depends on TensorFlow's features and functions, will run correctly and be compatible with the installed library. We begin by importing 3 standard Python libraries that handle files and directories. The operating system library lets us interact with the system to work with file paths and folders. The path library provides a more intuitive, object-based way to manage those paths. The high-level file operations library is used for tasks like copying and deleting directories. Together, these tools support all the file system operations used later in the script. We start by importing TensorFlow, which we use to build and train machine learning models. Within TensorFlow, we bring in Keras, a high-level interface that makes it easier to define neural networks. We then import the layers tools from Keras, which provide components such as dense layers that form the structure of our model. Setting a deterministic random seed in TensorFlow makes all random operations produce the same results every time you run the code. This is important because it ensures reproducibility, so you can reliably repeat experiments. Consistent outcomes are especially useful when you are debugging or comparing model performance across different runs. This code displays the version of TensorFlow currently in use. Knowing the exact version helps you check compatibility with your project. It also tells you which features and syntax are available, since different TensorFlow versions can behave differently. We define a small Keras sequential model as a simple feed-forward neural network. It takes input data with 4 features, then passes them through a dense layer with 4 neurons that use the ReLU activation function to add nonlinearity. After that, the model uses a final dense layer with a single neuron and a sigmoid activation function. This last layer outputs a probability, making the model suitable for binary classification tasks. Before training, the model is compiled by choosing how it will learn and how its performance will be measured. Here, the optimizer is set to Atom, a common and efficient method for adjusting model parameters, especially with large datasets. The loss function is set to binary cross-entropy, which is appropriate for binary classification, and indicates how well the model is distinguishing between the 2 classes during training. We create a very small dataset using TensorFlow by defining a constant with 2 samples, each having 4 features. The first sample is a vector of 4 zeros, and the second is a vector of 4 ones. We set the data type to float 32 so it works smoothly with TensorFlow operations. This simple dataset serves as input for training our model in a basic demonstration. We create a small tensor to hold the binary labels that our model will learn to predict. Using TensorFlow's constant function, we define a 2-dimensional tensor containing zeros and ones with a shape that matches the number of input samples. We set its data type to float 32 so it is compatible with the model's expected input format. This labeled tensor serves as the target output during training and is essential for guiding the learning process. The model is trained using a fit function that takes the input data and their labels, and it runs for 5 epochs, meaning it passes through the entire dataset 5 times to update the model's weights. Pausing briefly, during this process, the verbose setting is turned off, so no training progress is printed. This configuration allows you to train and refine the model quickly without filling the console with detailed output. The code uses the pathlib library to create a base directory called SavedModel demo, which serves as the main location for exporting the model. This directory path is stored as an object, so it can be reused whenever the model needs to be saved. Setting up this path in advance keeps the export process organized and makes the saved model easy to find and manage later. The code first checks whether the export directory already exists. If it does, it deletes that directory and everything inside it using a file handling library. This step clears out any previous model exports so they do not interfere with the new one. As a result, the current model is saved into a clean directory without leftover files from earlier runs. We use a TensorFlow function decorator to define how our model is served, including an input signature that expects a tensor with any number of rows and 4 float columns. Inside this function, the input tensor is passed through the model to generate predictions. The function then returns a dictionary, whose probabilities entry contains these prediction values. This structure clearly defines the input and output formats, which is important so external systems can reliably send data to the model and read its results. This code saves the model in the TensorFlow SavedModel format, which is well suited for production because it stores both the model's structure and its trained weights. The model is written to a directory defined elsewhere in the program. Although the comments note that the signatures setting does not affect exports in the 3rd version of Keras, they emphasize that you still need to match the actual output key when defining export signatures. Doing this ensures the model's serving function is correctly set up for later deployment and use. This code checks what is stored in the export directory by using the operating system tools to read its contents. It collects all the entries at the top level of that directory and sorts them alphabetically, so the order is consistent each time. It then prints this sorted list, letting you see which files and folders are present there. To find version subdirectories in the export directory, we start by listing all entries in the base export location. From this list, we keep only those entries that are actual directories. These directories correspond to different saved model versions. Identifying them in this way makes it easier to inspect, compare, or manage the various model versions. This code lists the names of the versioned folders inside the export directory and prints them in alphabetical order. By organizing and displaying these folder names, it makes it easy to see which version subdirectories are present. This provides a quick way to verify the structure of the saved model directory and confirm which model versions have been saved. To inspect a saved model, we focus on its version subdirectories. We start by sorting the list of version folders we previously found, then choose the first one in this sorted list. This folder represents the most recent or otherwise relevant version of the model. We store its path in a variable, so we can easily open it and examine the files inside that specific version directory. We now look inside the selected version folder of the saved model to see what it contains. By using the operating system's directory listing, we collect and sort the names of all files in that folder. This gives us an organized view of the files that make up this specific model version. Understanding these contents helps us see the structure and components of the saved model at this version level. The code builds the path to the variable subdirectory inside the chosen version folder of the saved model by joining the version folder path with the variable's directory name. This combined path represents where the model's variable files are stored. It will be used later to check whether those variable files exist as part of the model's saved state. The code first checks whether the directory that stores variables exists. If it does, it uses a function from the operating system module to list all files in that directory. It then sorts these file names in alphabetical order. Finally, it prints the sorted list so you can clearly see which variable files are stored in the saved model subdirectory. The code builds the path to the assets subdirectory inside a specific version folder of a saved model by combining the version folder path with the assets directory name. This is done as part of examining the saved model's directory layout. The goal is to see whether there are any asset files stored with the model that might be needed when it is loaded or used. The code checks whether an assets folder exists inside the versioned saved model directory, and if it does, lists and prints the files it contains. This reveals what additional resources are packaged with the model. If the assets folder is missing or has no files, the code instead prints a message stating that it is absent or empty. This helps confirm whether any extra model resources are present. We load the previously saved model from disk using TensorFlow's SavedModel loading function so we can use it again. This step restores the model in its saved model format, making it available for inference or further examination. Converting the export base path to a standard string ensures it is compatible with the loading function and allows the model to be reloaded correctly. The code uses the model's default serving signature to run inference on sample input data after the model has been reloaded. This serving signature is the predefined entry point created when the model was exported. The input tensor is passed into this serving function to produce the model's output. Doing this confirms that the saved model can be correctly loaded and still used for inference. The code checks the keys in the output of the reloaded model's default serving function to see what outputs the model produces when it is called. By listing these keys, you can identify the different parts of the model's output. This helps confirm that the model was reloaded correctly and that it is returning the expected results. We begin by finding the first key in the output dictionary produced by the reloaded model, which points to the model's output tensor. We then display the shape of this tensor. This shape tells us the dimensions of the probability values generated by the model and helps us understand the structure of its output. This material explains a short example of creating, saving, and reloading a TensorFlow model using the saved model format. A small neural network with dense layers is built, compiled with the Atom optimizer and a binary cross-entropy loss, then briefly trained on a simple dataset. After training, the model is saved into a directory, and the script inspects the saved model folder structure, including version subdirectories, variables, and assets. Finally, the model is loaded back from disk. Its default serving function is called with sample input, and the output keys and probability tensor shape are printed to confirm that saving and reloading worked correctly. Serving signatures overview. Serving signatures describe how a saved model handles inputs and outputs when it is deployed. When TensorFlow exports a model, it not only stores the weights and computation graph, but also records named signatures that define which functions are available for serving. A common example is a prediction signature that maps input tensors, such as tokenized text, to output tensors like class probabilities. These signatures act as contracts between the model and external systems by specifying input and output shapes, data types, and names. This allows other platforms to integrate with the model reliably without having to understand its internal details. A saved model can define multiple named signatures, each tailored to a different use case while sharing the same underlying weights. For example, a computer vision model might expose one signature for raw image tensors used in batch processing and another for pre-processed data in analytics workflows. A recommendation system might similarly provide separate signatures for real-time ranking and offline evaluation. These names allow serving systems such as TensorFlow Serving to route each client request to the appropriate signature so the client receives the expected behavior and data format. When designing serving signatures for a model, focus on how it will be used in real-world applications, not just in training. Decide which pre-processing steps should happen inside the signature, and choose clear names for inputs and outputs. For instance, a fraud detection model might take transaction details and return a risk score and a decision flag. If you keep this signature stable, even when the model architecture changes, the surrounding system does not need to be updated. This separation lets teams improve models while keeping application integration consistent and reliable. Python code, serving signatures overview. This script introduces basic TensorFlow SavedModel signatures using a simple Keras model. It demonstrates how to export a Keras model as a saved model and then load it again. The focus is on understanding the core steps of saving and restoring models. You are expected to run the cells in order, and it is designed to work smoothly in Google Colab. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. It is commonly used in environments like Google Colab to make sure that this exact version of TensorFlow is available. Specifying the version helps ensure the script runs correctly and prevents compatibility problems that could occur with a different version of the library. We start by importing the operating system library so we can interact with the file system. For example, to check whether files exist or to create folders. We also import the pathlib library, which gives us a convenient object-oriented way to work with file paths across different operating systems. Finally, we bring in the numerical computing library NumPy, which we will use to create and manipulate arrays and to perform mathematical operations efficiently. We begin by importing TensorFlow, a main library used for machine learning and deep learning. We then import Keras, a high-level interface within TensorFlow that makes it easier to build and train neural networks. Finally, we bring in the layers tools from Keras, which provide different types of neural network layers for constructing models. These imports give us the essential components needed to create and manage deep learning models efficiently. This code simply prints the version of TensorFlow that is currently in use. Knowing the exact version helps you check compatibility with other tools and libraries. It also tells you which features and syntax are available, since different TensorFlow versions can behave differently. To make our code give the same results every time it runs, we use a fixed random seed. We choose a specific seed value, such as 42, and apply it to the random number generator in NumPy. We then set the random seed in TensorFlow using the same value so that both libraries produce consistent random behavior. This reproducibility is important for debugging and for reliably comparing results across different runs. This code uses TensorFlow's configuration tools to check whether any GPU devices are available on the system. It looks up all physical devices of type GPU and counts how many it finds. It then prints the number of detected GPUs, which tells you if TensorFlow can use GPU acceleration and how much GPU hardware is available for running its computations. We begin by creating a small numeric dataset with 8 samples. Using a numerical tool, we generate 8 evenly spaced values ranging from -1 to 1. These values are then reshaped into a single column, forming a simple input dataset that will be used to feed our model. We generate target values for our dataset using a simple linear transformation of the input data. For each data point, we multiply the value by 2 and then add 0.5. This transformed result becomes the target value. Finally, we convert these targets to the float32 data type, so they are compatible with TensorFlow operations. Before building the model, the code prints the shapes of the input and target data to confirm that their dimensions are correct. This check ensures the data matches the model's expected input and output structure. Verifying these shapes helps catch mismatches early and prevents errors during training and evaluation. In short, it is a quick way to confirm that the data is properly organized before running the model. We build a simple Keras sequential model as a straight stack of layers. It starts with an input layer that takes data with one feature, followed by a dense layer with 4 neurons using a ReLU activation to add nonlinearity. The final dense layer has a single neuron that produces the model's output. This kind of architecture is commonly used for regression tasks where we want to predict a continuous value. The model is set up for training using the Atom optimizer, a common and efficient method for updating neural network weights. It uses mean squared error as the loss function, which is standard for regression tasks because it measures the average squared difference between predicted and actual values. Together, this optimizer and loss function define how the model learns from data and how its performance is evaluated during training. The model is trained using a fit function that takes input data and target values and adjusts the model's parameters. It runs for 50 epochs, meaning it passes through the entire dataset 50 times during training. The verbose setting is turned off, so no progress messages are printed while it trains. This silent setup is useful when you want quick, clean training runs without detailed feedback. Before saving the model, we first generate a baseline prediction. We create a small numeric array, containing the value 0.25 as a 32-bit floating point number, and use it as the input. We then call the model's prediction function with output turned off, so it runs quietly. The resulting value is stored as the original prediction, which we will later compare with predictions made after the model is saved and reloaded. The code prints the model's original prediction by taking the first value from the prediction array, converting it to a floating point number, and outputting it. This recorded value serves as a reference point. Later, when the model is saved, reloaded, and used to make new predictions, this original prediction can be compared to the new ones. Doing so helps confirm that the model's behavior remains consistent after saving and loading. We define a serving function using TensorFlow's function decorator with an input signature that specifies the expected input shape and data type. Here, a tensor with any number of rows, one column, and 32-bit floating point values. This serving function, called serveRegression, takes the input features, feeds them into the model, and obtains the outputs. It then returns a dictionary whose prediction entry contains these outputs. This clear serving signature is essential for exporting the model so that inference uses consistent and well-structured inputs. We begin by setting up a directory where the saved model will be exported. Using a path object, we point to a folder named for storing the model signatures. We then check whether this folder already exists, and if it does, we leave it as is. This simple setup step ensures there is a dedicated location ready for saving the model later in the script. We save the Keras model using TensorFlow's SavedModel format by choosing a directory and converting its path into a string suitable for file operations. A crucial step is defining the serving signatures, which describe how the model will be used for inference. We assign the default serving signature to a custom function called serveRegression. This function defines how input data is handled during prediction, so that when the model is loaded later, it knows exactly how to process incoming data to produce outputs. We first define a path for saving the model's weights by combining the export directory with a file named weights-only.weights.h5. Then we save the model's weights to this location. Saving just the weights separately from the full model creates a standalone file that contains only the learned parameters. This is useful when we only need to transfer or store the model's parameters without including the entire model architecture. This code loads a previously saved TensorFlow model from a chosen directory using the SavedModel loading function. The model is restored as a general trackable object, which means it can be managed and inspected by TensorFlow. Once loaded, you can access the model's available serving signatures and use them to run inference or other operations. The code displays the available signatures from a loaded saved model by reading its signatures attribute, which is a dictionary of callable functions prepared for serving. By listing the keys of this dictionary, you can quickly see which functions are exposed for inference. This step helps you understand what operations the saved model can perform when you use it for prediction or other serving tasks. Here, we retrieve the default serving signature from the loaded saved model, which is a predefined function used to run inference. This function captures how the model is meant to receive inputs and produce outputs. By accessing it, we can later pass in new data to generate predictions. This ensures that we use the model in the same way it was originally configured and saved for serving. We create the input tensor for the serving function by building a dictionary with a single key called features. This key points to a TensorFlow constant that is a two-dimensional array filled with the value 0.25. The tensor is explicitly set to use the float32 data type. This structure ensures the input matches the serving function's expected signature, so it can process the data correctly. The code uses the serving function from the TensorFlow SavedModel to generate predictions. This function is accessed through the loaded model's signatures and is given a prepared input tensor with the correct features and shape. It then returns the model's predictions. Running this step confirms that the saved and reloaded model can still perform inference correctly. We obtain a numeric prediction by working with the dictionary returned from the TensorFlow serving function. This dictionary has a key named prediction that stores a tensor. We take the first element of that tensor, convert it into a NumPy array, and then cast it to a standard floating point number. The result is a single float value that is ready to be used for comparison or further analysis. We first print the prediction produced by the saved and reloaded model to confirm that it behaves the same as before. Then we compare this served prediction to the original prediction made prior to saving. By printing the difference between them, we can spot any discrepancies. This process helps verify that the model's predictions stay consistent, stable, and reliable across saving and loading steps. We first create a directory path using a path handling library and name it as the location where the Keras model will be stored. Then we call the model.save method to write the model to this directory. This saves both the model's architecture and its learned weights in the TensorFlow SavedModel format. Using this format makes it easy to load the model later for inference or to continue training. The code verifies that the directory containing the saved Keras model actually exists. If it does, it prints a confirmation message. This check helps ensure that the model export was successful and that the saved model is available for later use or verification steps. This script shows how to export and reload a simple Keras regression model using TensorFlow's SavedModel format. It builds and briefly trains a small model on a toy dataset, then makes an initial prediction for later comparison. The model is saved with a serving signature, so it can be reloaded and used for inference. And after loading, the script checks the available signatures and runs a prediction through the serving function. It compares the original and reloaded predictions to confirm they match, also saves the model in Keras format, verifies the export directory, and uses fixed random seeds and GPU checks to keep the process reproducible. Model versioning strategies. When exporting models for production, avoid repeatedly overwriting the same directory. Instead, save each export in its own version directory, using a unique identifier such as a number or timestamp. This makes it possible to track and compare different model versions over time, which is important for debugging, auditing, and meeting regulatory requirements. For example, a recommendation system might store a new model every night, creating a clear history of changes. Keeping versions separate supports understanding how the model has evolved and ensures traceability and reproducibility. When managing model versions, it is important to organize saved model exports in a way that matches the serving system's expectations. Tools like TensorFlow Serving use separate subdirectories for each version of a model, so they can load either the latest version or a specific one. For example, a fraud detection model might have a directory for each training run. This structure lets operations teams gradually shift traffic to a new version, while keeping older versions available as backups. As a result, they can safely test new models in production and quickly roll back if problems occur. In advanced workflows, combining rich semantic labels with saved model versioning makes it easier for data science, engineering, and compliance teams to work together. For example, a healthcare company might tag each exported model with its family, data snapshot date, and training setup, while storing more detailed metadata elsewhere. This approach lets teams trace which exact model version produced predictions at a given time or before certain data changes. In regulated fields like finance, this traceability is essential for audits, and even in less regulated areas, Disciplined versioning improves experimentation, communication, and deployment by giving everyone a clear reference for each model. Keras model saving. Model save options. When deploying Keras models, you must choose how to save them. You can save the entire model, which stores both the architecture and the learned parameters, making it easy to load and use immediately. Alternatively, you can save only the weights and later rebuild the architecture yourself, giving you more flexibility to change the model design. This decision affects how portable your model is and how easily others can use it without needing to know the details of how you developed it. When deciding how to save your Keras models, think about how they will be used and how the model may change over time. For deployed models, such as those running in services or mobile apps, it is usually best to save the entire model so it can be loaded easily in different environments without needing the original code. In research settings, it can be more useful to save only the weights at different checkpoints, which lets you modify the model architecture while keeping the learned parameters. This approach supports hyperparameter tuning and experimenting with new ideas without losing training progress. When training models, it is important to decide how often to save intermediate versions and how to use them. During long training runs, you usually save checkpoints that store only the model weights to reduce storage. After you identify a checkpoint that performs well on validation data, you can keep it for further experiments or turn it into a full model for deployment. This strategy conserves resources, protects against hardware failures, and still gives you a complete model ready for production. Python code model save options. This script introduces the basics of saving models in Keras. It focuses on two main ideas: how to save the entire model and how to save only the model's weights. To get the most out of it, you should run the cells in order, so each concept builds on the previous one. By the end, you will understand the core approaches to preserving Keras models for later use. The line starting with an exclamation mark is a shell command that installs TensorFlow version 2.20.0. Specifying this exact version helps ensure the code runs with the expected library behavior, which is important for compatibility and reproducible results. The exclamation mark indicates that this command is intended to be executed directly in a Jupyter notebook or a similar environment that allows running shell commands. We begin by importing TensorFlow, which includes the Keras high-level neural network interface. This import is essential because it provides the tools needed to build, train, and save machine learning models. TensorFlow is a widely used deep learning library, and Keras makes it easier to create complex models through a more user-friendly interface. Together, they form the foundation for our model development workflow. We set a deterministic seed using TensorFlow's Keras tools so that any random operations behave the same way every time the code runs. This makes the results repeatable, which is called reproducibility. Reproducibility is important because it lets us get consistent outcomes across different runs. It is especially useful when debugging models or comparing their performance, since we know differences are due to changes in the code or data. This line displays the version of TensorFlow currently in use. It provides a quick check that your environment is running the expected TensorFlow version. Confirming the version helps ensure that the features and functions you rely on will work correctly in your script. We begin by loading a small subset of the MNIST dataset using tools from TensorFlow's Keras library. MNIST consists of images of handwritten digits that are widely used to train image recognition models. The data is divided into a training set, which is used to teach the model, and a test set, which is used later to measure how well the model performs. This data loading and splitting step is essential for preparing the information needed to train and evaluate our machine learning model. To quickly demonstrate the model, we limit the training data to the first 2,000 samples. This smaller subset speeds up the training process, making it easier to run and experiment with. Even with fewer samples, it still allows us to clearly illustrate the main ideas and concepts behind the model. The code converts the training images to floating point numbers and scales their pixel values to range from 0 to 1. This normalization keeps all inputs on a consistent scale, which is important for neural networks. It helps stabilize training and allows the model to learn and converge more efficiently. We add a new dimension to the training data, so it matches the input shape required by convolutional layers in Keras. The original data is missing the channel dimension that convolutional neural networks expect for image processing. By using TensorFlow to expand the data along a new axis, we create this channel dimension. This adjustment makes the training data compatible with the two-dimensional convolution layers that come next. We print the shape of the training subset to confirm it matches what we expect. This quick check helps verify that pre-processing steps, such as normalization and adding the channel dimension, were applied correctly. By confirming the data shape, we make sure the input is in the proper format before starting model training. This reduces the chance of errors later in the training process. We build a simple sequential model in Keras for classifying MNIST digit images. It starts with a two-dimensional convolutional layer with 8 3x3 filters and ReLU activation, taking 28 by 28 grayscale images as input. A 2x2 max pooling layer then reduces the spatial size of the feature maps, and the result is flattened into a one-dimensional vector. This feeds into a dense layer with 16 units and ReLU activation, followed by a final dense layer with 10 units and softmax activation. The output layer produces a probability for each of the 10-digit classes, allowing the model to classify the input images. The model is trained using the Atom optimizer, chosen for its efficiency and low memory use. It uses sparse categorical cross-entropy as the loss function, which is appropriate for multi-class classification when the labels are given as integers. During training, accuracy is tracked as a key metric to evaluate how well the model is performing. The model is trained using the fit method, which takes the small training dataset and its labels as input. Training runs for 2 epochs, so the model goes through the entire dataset twice. A batch size of 64 is used, meaning the model updates its weights after every 64 samples. The verbose setting is 0, so the training runs without printing any progress to the console. We take a small batch from the training data, using just the first 5 samples, and use this subset to compare model predictions. By running different versions of the model on the same small batch, we can directly check whether their outputs match. This helps us confirm that saving and loading the model preserves its behavior and ensures consistency across versions. The trained model is used to make predictions on a small sample taken from the training data. A prediction function is called on this sample with extra output turned off, so it runs quietly. This produces the predicted probabilities for each class, which are stored for later use. These stored predictions will be compared with predictions from other saved and reloaded versions of the model to check that they are consistent. The code prints the predicted class labels produced by the original model. It takes the previously computed prediction probabilities for each sample in the batch and uses a function that selects the index of the highest value along the class dimension. This index represents the most likely class for each sample. The code then outputs these class indices to the console, showing the final predicted classes for all processed samples. We first choose a file path for saving the entire model, which includes both its architecture and its learned weights, in a single, full model file. We then choose a second file path for saving only the model's weights in a separate weights file. Having these two saved files is important because it lets us reload either the complete model or just its weights later, without needing to train the model again from scratch. This code saves the entire TensorFlow Keras model, including both its architecture and learned weights, to a file. It uses the save method and turns off saving the optimizer state by setting the include optimizer option to false. Skipping the optimizer state makes the file smaller and is usually fine if you do not need to resume training from that exact point. Later, you can reload this saved model fully and use it for inference or continue training as needed. This code saves only the model's learned weights using the TensorFlow Keras method, storing them in a checkpoint file. By doing this, it preserves the trained parameters without including the full model architecture or the optimizer state. This approach reduces storage requirements and makes it possible to load the saved weights into another model that shares the same architecture at a later time. We reload the full model from the directory where it was previously saved so we can use it again. TensorFlow's model loading function rebuilds the model structure and restores its trained weights. This means the model behaves exactly as it did before saving. Once loaded, it can be used immediately for making predictions or for continuing training. Next, we use the fully loaded model to generate predictions on the sample batch. We pass the sample data through the model and collect the resulting outputs as our predicted values. These predictions are stored for later use while the verbose setting is turned off so that the prediction process runs quietly without detailed logging. This keeps the operation efficient and focused only on producing the outputs we need. To display the predicted classes from the fully loaded model, we take the stored prediction outputs and, for each sample in the batch, identify the position of the largest value along the last dimension. This position corresponds to the class with the highest predicted probability. We then print these class labels so we can compare the model's predictions with those from other models. To load previously saved weights, we first recreate the same Keras model architecture. We build a sequential model that starts with a two-dimensional convolutional layer using 8 3x3 filters with ReLU activation, taking 28x28 grayscale images as input. This is followed by a max pooling layer that downsamples the feature maps, then a flattening step that converts them into a one-dimensional vector. We then add a dense layer with 16 units and ReLU activation, and a final dense layer with 10 units and softmax activation to produce class probabilities. Matching this architecture to the original model ensures the saved weights can be loaded correctly. We compile the recreated model so it is ready to load and use the saved weights. In this step, we choose the Atom optimizer, which is commonly used for training neural networks efficiently. We set the loss function to sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are integers. We also track accuracy as a metric to monitor how well the model performs during training and testing. Once compiled, the model is prepared to process data and update its weights. Next, we load the previously saved weights into the recreated model. This step transfers the learned parameters from the original model to the new one, so it can make predictions as if it had been trained from the beginning. By doing this, we avoid retraining on the data while still preserving the model's learned behavior. As a result, the recreated model should match the performance of the original model. We now use the recreated model, which has the same architecture as the original and has been loaded with the saved weights, to make predictions on a sample batch. By calling the prediction function with the verbose setting turned off, the model generates outputs without extra logging. This step verifies that the model with loaded weights behaves the same way as the original model, and produces matching predictions. This code prints the predicted classes from a model that has been rebuilt using only its saved weights. It takes the model's output predictions and selects the index of the largest value along the last dimension, which represents the predicted class for each sample. By comparing these predicted classes to those from the original model, you can confirm that loading the saved weights successfully reproduces the same predictions. We verify that all three sets of model predictions match by comparing the predicted classes from each version of the model. For each prediction, we take the class with the highest probability and check whether the original model and the fully loaded model choose the same class for every example. We repeat this comparison between the original model and the model that only loaded the weights. Finally, we confirm that both comparisons are true at every position, which shows that all three models produce identical predictions. This script shows how to save and load a Keras model in TensorFlow using a small example with the MNIST dataset. After preparing and briefly training a simple convolutional neural network, it first saves the complete model, including its architecture and weights, and also saves the weights alone. The script then reloads the full model from file and checks that its predictions match those of the original model. It also rebuilds the same model architecture from scratch, loads only the saved weights, and verifies that this version produces identical predictions. Overall, it demonstrates that both full model saving and weights-only saving work correctly and preserve the model's behavior. HDF5 and saved model. When saving a Keras model, you can use either the older HDF5 format or the newer TensorFlow SavedModel format. HDF5 creates a single compact file that is convenient for sharing and moving between environments. SavedModel, on the other hand, creates a structured folder that integrates closely with TensorFlow and is the default when you do not specify a format. Because of this integration and its support in TensorFlow serving tools, SavedModel is generally recommended for modern production deployments. The HDF5 format is popular because it is simple, has been used for a long time in areas like physics and bioinformatics, and stores everything in a single file that is easy to manage and share with tools outside TensorFlow. Research teams often use it to save model snapshots so they can roll back or compare performance. However, it is mainly designed for Keras models and focuses on layers and weights rather than the full TensorFlow execution model. As a result, it is less suitable when you need tight integration with TensorFlow serving tools or deployments that span multiple programming languages. The saved model format is designed for smooth deployment and integration across the TensorFlow ecosystem. It stores models in a directory that includes the computation graph, variable checkpoints, and extra assets, so the same model can be used by Keras, TensorFlow Serving, TensorFlow Lite, and non-Python clients such as Java or C++. This makes it well-suited for deploying models as web services, embedding them in mobile apps, or plugging them into data pipelines, and allows a team to train a model in Python and hand it off for deployment without changing the training code. Compared with HDF5, which is mainly convenient for Keras workflows, SavedModel is the preferred choice for robust, production-ready deployments. Python code, HDF5, and SavedModel. This lesson demonstrates the basics of saving Keras models. It focuses on comparing the HDF5 format with the SavedModel format. It also shows how to reload saved models and verify that their predictions remain correct after loading. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. It forces the environment to use this exact version so the code remains compatible and avoids problems that might appear with newer releases. The exclamation mark shows that this is a shell command intended to be run directly inside a Jupyter Notebook or a similar environment that supports such commands. We begin by importing 3 key Python libraries. The operating system library lets us work with files, folders, and other system features. The pathlib module provides a more intuitive, object-based way to handle file paths. Finally, the numerical computing library NumPy is used to create and manipulate arrays, which will be central to the calculations in this script. We begin by importing TensorFlow, a main library used for machine learning and deep learning. Within TensorFlow, we use Keras, a high-level interface that makes it easier to build and train neural networks. We also import the layers tools from Keras, which provide essential components like dense layers and activation functions. Together, these imports give us the basic tools needed to create and manage our machine learning models. This code displays the version of TensorFlow that is currently installed and running. Knowing the exact version helps you check compatibility with other tools and libraries. It also tells you which features and improvements are available in your environment. This is important because different TensorFlow versions can offer different capabilities. We begin by setting fixed random seeds for both NumPy and TensorFlow so that any random numbers they generate are the same every time the script runs. This makes the behavior of the code predictable and repeatable. It is especially important when training machine learning models because it allows you to reproduce the same results across different runs and reliably compare experiments. To build a simple regression example, we first create a small synthetic dataset. We generate 200 evenly spaced values between -1 and 1 using a numerical tool that creates linear sequences. These values are then converted to the float32 data type, which is commonly used in machine learning to work smoothly with TensorFlow and to reduce memory usage. This prepares a clean, efficient set of input values for later modeling steps. We create target values for our regression model by applying a simple linear transformation to the input data. Each input is multiplied by 3 and then increased by a constant value of 0.5. To make the data more realistic, we add a small amount of random noise drawn from a normal distribution and scaled so its effect stays minor. Finally, we convert the result to 32-bit floating point format to keep it compatible with TensorFlow operations. We reshape the input and output data into column vectors so they match the format the model expects. The model requires data in 2 dimensions, with each row as one sample and each column as one feature. By converting the arrays into this structure, we align the data with the model's input requirements. This ensures the model can be trained correctly and make proper predictions. Before training a model, it is important to print the shape of the input data to confirm that the features are arranged correctly so the model can process them properly. We also print the shape of the target data to make sure each input has a matching output value. Checking these shapes helps verify that the inputs and targets are aligned and that the data preparation steps are correct. This simple check is an essential part of debugging and validating the data before starting model training. We build a simple sequential model in Keras for regression, where the goal is to predict a continuous value. The model takes inputs with a single feature, then passes them through a dense layer with 8 neurons using a ReLU activation to capture nonlinear patterns. It ends with a dense layer that has 1 neuron, which produces the final predicted value. This structure is a common and straightforward choice for basic regression tasks. The model is compiled using the Atom optimizer a common choice in deep learning because it is efficient and automatically adjusts the learning rate. The loss function is mean squared error, which is typically used for regression tasks and measures the average squared difference between predicted and actual values. Together, these choices define how the model updates its weights and how its performance is evaluated during training. The model is trained using a fit procedure, where it learns from paired input and target data. Training runs for 20 epochs, meaning the model goes through the entire dataset 20 times. The data is handled in batches of 32 samples at a time, which controls how much data is processed in each step. The training is set to run silently, with no progress messages printed during the process. We create a small test batch of input values to check the model's predictions. This batch includes three numbers, -1/2, 0, and +1/2. They are stored together in a NumPy array using the float32 data type. Using this simple set of inputs makes it easier to see how the model behaves and to interpret and compare its predictions. The code first runs the original model on a small set of sample inputs to create a baseline for later comparison. It calls the model's prediction function on these samples while turning off extra output, so the process stays quiet. The resulting predictions are saved so they can be compared with predictions from models that are reloaded or modified later. We start by defining a base directory using a tool that handles file paths in a way that works on any operating system. And we name this directory SavedModels Demo. Next, we create this directory only if it does not already exist, using an option that prevents errors when the directory is already there. This gives us a reliable, dedicated location where we can store our saved models without worrying about compatibility or repeated creation. We set up a file path to save the model in HDF5 format by combining a base directory used for storing models with the file name for the linear regression model. This creates a clear, consistent location where the model file will be stored. Using this organized path makes it easier to find, manage, and reuse the saved model later. This code saves the entire Keras model in the HDF5 format by calling the model.save function and giving it a storage location. In this case, the option to include the optimizer is turned off, so the optimizer's internal state and training configuration are not stored. As a result, only the model's architecture and learned weights are saved, which is useful when you do not need to resume training and only care about using the trained model for inference. We set up a path to save the model in the saved model format by combining a base directory with a specific model name. This path points to the location where the trained model will be stored. Saving in this format allows TensorFlow to reload the model later. This ensures the model remains compatible with TensorFlow tools and is easier to deploy in different environments. This code saves the full Keras model using the saved model format, which is flexible and can be loaded in different TensorFlow environments, including TensorFlow Serving and TensorFlow Lite. The model is written to a chosen location, making it easy to deploy or reuse later. When saving, it leaves out the optimizer state, which is fine if you do not need to continue training from exactly where you left off. We are saving only the model's weights to a separate checkpoint file. To do this, we first define a storage location by combining a base directory with a specific file name for the weights. Then we call the model's SaveWeights function and pass in this location. This stores the learned parameters so we can reload them later without needing to save or reconstruct the full model architecture or optimizer settings. We are loading a previously saved model from an HDF5 file using Keras, so we can restore it exactly as it was. This process reloads both the model's architecture and its learned weights from the file. Once loaded, the model can be used right away for making predictions or for continuing training. This avoids the need to redefine the model or train it again from the beginning. We can reload a previously saved Keras model by using the Keras model loading function and giving it the path to the saved model directory. This restores both the model's architecture and its learned weights. Once loaded, the model is ready for making predictions or for continuing training. This avoids the need to redefine the model or train it again from the beginning. We build a new Keras sequential model as a simple stack of layers. It starts with an input layer that takes data with one feature, so the input is one-dimensional. Then we add a dense layer with 8 neurons using our ReLU activation function to introduce nonlinearity. Finally, we add a dense output layer with a single neuron to produce the prediction. This architecture matches the original model, so we can later load the previously saved weights into it. Before loading saved weights into a model, you must first compile it using the atom optimizer and mean-squared error as the loss function. Compiling prepares the model so it can accept the weights correctly. This ensures that the optimizer and loss function are properly configured. As a result, the model is ready for any further training or evaluation after the weights are loaded. This step loads the previously saved weights into the model that was built earlier. By doing this, the model recovers the parameters it learned during training without having to train again. As a result, it can immediately make predictions as if it had just been trained from scratch. This ensures consistent behavior while saving time and computational resources. We now use the model that was reloaded from the HDF5 file to generate predictions on a small batch of sample inputs. The prediction method is called with these inputs, and the verbose setting is turned off, so no extra output is produced. This step is important because it lets us check that the reloaded model gives the same predictions as the original one. Matching results confirm that the model's integrity has been preserved through the saving and loading process. We now use the model that was reloaded from the saved model format to make predictions on small batches of sample data. These inputs are passed into the reloaded model, which computes outputs in silent mode without showing progress messages. This step is important because it lets us confirm that the reloaded model behaves the same way as the original one. If the predictions match, we know the save and reload process preserved the model's behavior correctly. The code tests a model that has been reloaded using only its saved weights by making predictions on a small set of sample inputs. This check confirms that the reloaded model still behaves like the original and produces consistent outputs. The verbosity setting is turned off, so the prediction step runs quietly without extra diagnostic messages, and only the final results are shown. This part of the code defines a helper function called the maximum absolute difference function, which calculates the largest absolute difference between two arrays. It uses numerical operations to compare corresponding elements in the arrays, finds the biggest absolute difference, converts that value to a standard floating point number, and returns it. This function is useful for checking how much predictions from different models differ from each other. We now compare the original model's predictions with those from each reloaded version by computing the maximum absolute difference between them. We first measure this difference for the model reloaded from the HDF5 file, then for the model reloaded from the saved model format, and finally, for the model restored using only the saved weights. These comparisons allow us to confirm that all reloaded models produce predictions that are consistent with the original model. We begin by printing the model's original predictions, rounded for clarity, to establish a baseline. Then, we measure the maximum absolute difference between these predictions and those from a model reloaded using the HDF5 format to see how closely they match. We repeat this process for a model reloaded with the saved model format and for a model restored using only saved weights. Comparing these maximum differences lets us check how consistent the predictions are across different saving and loading methods, and helps verify the reliability of the model persistence process. This script shows how to save and load a Keras regression model using different formats, and then verify that they preserve the model's behavior. A simple model is trained on synthetic data and saved as a full model in HDF5 format, as a full model in the saved model format, and as weights only. Each version is then reloaded and used to make predictions on a small sample input. The script compares these predictions with those from the original model and prints the maximum absolute differences. The results demonstrate that all three saving methods reliably reproduce the original model's predictions. Loading custom objects. When you build models with custom architectures, activations, layers, or training logic, saving and loading them requires extra care. Keras does not automatically recognize these user-defined components, so you must explicitly map the saved configuration back to the correct Python objects in your code. If you skip this step, the model may fail to load or lose important behavior. In a production setting, such as fraud detection with a custom feature scaling layer, this can lead to inconsistent predictions and incorrect risk assessments. To safely reload models that use custom components, those components must be registered and structured so they can be serialized and discovered later. Their configuration should be described using simple data structures, such as dictionaries, so the system can save this description along with the model's weights. When the model is loaded, the framework reads this stored configuration and uses it to reconstruct the exact same custom layers and activations. This process ensures that specialized mechanisms, such as a custom attention module in a medical imaging model, are restored accurately and preserve their validated behavior. Managing custom objects in machine learning models is essential when those models are shared, deployed, or archived for later use. If a custom layer is not correctly defined in the environment, the model may fail to load, disrupting research and deployment. By establishing clear conventions for defining and registering these components, teams keep models consistent and reliable over time, including during audits or new evaluations. Python code. Loading custom objects. This lesson demonstrates how to load custom objects with a focus on saving and restoring Keras models. It walks you through the key steps needed to handle models that include user-defined components. To follow along smoothly, you should run all the cells in order in a Colab environment. By the end, you will understand the basic workflow for saving and loading these customized Keras models. The script starts by making sure TensorFlow, specifically version 2.20.0, is installed, because this library is required for building and running the machine learning models in the code. The installation command is commented out so that users can run it only when needed, such as in environments like Google Colab, where TensorFlow may not already be available. This step helps ensure compatibility and avoids problems that can occur if a different TensorFlow version is used. We begin by importing three key tools for our work. The operating system module lets us interact with the system, for example, to set environment variables. NumPy provides efficient support for numerical computations, including working with arrays and generating random numbers. TensorFlow is then imported as the main machine learning library we will use to build and manage neural network models. To make our experiments reproducible, we fix all sources of randomness in the code. We set Python's hash seed to 0, so hash values stay the same across runs. We also set the random seed in NumPy to 0, so its random numbers are consistent each time. Finally, we set TensorFlow's random seed to 0, so operations like weight initialization behave deterministically. Together, these steps help ensure consistent results, which is important for debugging and fair comparison of models. This line of code displays the version of TensorFlow currently in use. It provides a quick check that your environment is running the expected TensorFlow version. Confirming the version helps ensure compatibility with the rest of your code. This simple step can prevent issues that arise from using an unexpected or incorrect library version. We create a custom scaling layer by defining a new class called custom scaling that inherits from the Keras layer base class. In its initialization method, we set a default scale factor of 1, which can be customized when the layer is used. The superclass initializer is called to handle any extra keyword arguments correctly, and the chosen scale factor is stored as an instance variable. This stored value is later used to scale the input data passed through the layer. In this custom layer, the call method takes the input data and multiplies it by a scale factor. This operation changes the magnitude of the input values as they move through the model. By adjusting this scale, the layer can transform the inputs in a way that supports and potentially improves the model's learning process. In this approach, we first call the parent class method that returns the current configuration settings. We then add our custom scale factor parameter to this configuration dictionary. After updating it, we return the modified configuration. This ensures that the custom scaling layer can be saved and later restored with its specific settings preserved. We build a simple model using a custom layer by first defining an input with 4 features in Keras. We then pass these inputs through a custom scaling layer that multiplies each value by a factor of 2. After that, we add a dense layer with 1 output neuron that uses a sigmoid activation, which is suitable for binary classification. Finally, we create the model by connecting the input through the scaling layer and then to the dense layer, forming a complete end-to-end network. The model is compiled with a specific optimizer and a loss function. It uses the atom optimizer, which is commonly chosen because it trains neural networks efficiently and adapts well during learning. The loss function is binary cross-entropy, which is appropriate for binary classification problems. This loss measures how different the model's predicted outputs are from the actual target values. We begin by creating a small synthetic dataset for training. Using a numerical library, we generate an 8x4 array of random floating point numbers to act as our input features. We then create an 8x1 array of random integers, either 0 or 1, to serve as the target labels. Both the feature and label arrays are converted to the float32 data type, so they are compatible with TensorFlow operations. Before training the model, we first confirm that the input and output data have the correct shapes. We check that the training inputs contain 8 samples, each with 4 features, and that the training outputs contain 8 samples, each with 1 target value. These checks act as safeguards to catch any mismatched dimensions early and help prevent errors during the training process. The model is trained using a fit function that takes the training data and their labels as input. It is run for 3 epochs, meaning it goes through the entire dataset 3 times. The training output is silenced by setting the verbosity to 0, so no progress messages are shown. This short training run is intended only to demonstrate how the model works, not to achieve high accuracy. We create a small batch of input data to use for model predictions by defining a NumPy array with 1 row containing the values 0.1, 0.2, 0.3, and 0.4. This array is given the float32 data type. Using this specific type keeps the data compatible with TensorFlow operations, which often expect float32 for efficiency and consistency. Before saving the model, we first run it on some sample input data to generate predictions. We do this by calling the model's prediction function with the sample data and turning off extra output so the process is quiet. These predictions are recorded so that after we reload the saved model, we can run the same inputs again and compare the results. Matching outputs confirm that the model was saved and restored correctly. We set up a directory path to specify where the trained model will be saved and store this path in a variable. By choosing this location, we make sure the model's structure and learned weights are written to disk in a known place. This is important so we can later load, reuse, or share the model. It is especially crucial when the model includes custom layers or configurations that must be preserved exactly for future use. The code first checks whether the target directory for saving the model already exists. If it does, it uses TensorFlow's input and output tools to safely delete that entire directory. This clears out any old model data before saving a new one. Doing so helps avoid conflicts or errors during the model saving process. This code saves the entire model, including its custom layer, into a chosen directory using the model's save function. It is configured so that the optimizer state is not saved, meaning only the model's architecture and learned weights are stored. This approach is useful when you want to deploy or share the model without including the training configuration or optimizer details. We first try to load the saved model without specifying any custom objects, storing the result in a variable if it works. This is wrapped in a try-except block so that if the loading fails, the error is caught instead of stopping the program. When an exception occurs, we print a message explaining that loading without custom objects did not succeed. This process shows that models using custom components usually require those custom objects to be provided again when the model is loaded. We load the model from the chosen directory and provide a mapping for any custom objects it uses. This mapping links the name of the custom scaling layer to its actual class definition. By doing this, TensorFlow knows how to rebuild that custom layer when loading the model. As a result, the model is restored with its custom layer fully intact, keeping its original behavior and settings. We now use the loaded model to generate predictions on the sample data to confirm that it works correctly after being reloaded with the custom layer. The sample input is passed to the model's prediction function, and the output is requested in a silent mode to avoid extra messages. These new predictions will later be compared with the original results to check that the model's behavior remains consistent. We first round and print the original model prediction so we can see its value before saving. Then we load the model with the custom layer, round the new prediction, and print it as well. Finally, we compute and print the difference between the original and reloaded predictions with higher precision. This comparison checks that the predictions match closely, confirming the model remains consistent after being saved and loaded. To verify that a custom layer type is preserved after saving and loading a model, we check the type of the second layer in the loaded model. We do this by accessing the model's list of layers and reading the class name of that specific layer. If the class name matches the custom scaling layer, it confirms that the layer has been correctly recognized and maintained through the save and load process. This script shows how to correctly save and load a Keras model that uses a custom layer. It defines a simple scaling layer, builds and briefly trains a small model on synthetic data, and then makes a prediction. The trained model is saved, and an attempt to reload it without telling Keras about the custom layer fails, demonstrating that custom objects must be specified when loading. When the model is reloaded with the custom layer properly registered, it produces consistent predictions, confirming that its behavior is preserved. The script finishes by checking that the loaded model still contains the correct custom layer type. Reloading and validating models. Loading saved models. When you return to a trained model, the first step is to load it from its saved state on disk into active memory so your application can use it again. A properly saved model includes its weights, architecture, computation graph, and any custom components. Loading it reconstructs the full predictive pipeline, so it handles inputs and outputs the same way it did before. Whether the model is stored on a server, in cloud storage, or in a model registry, the goal is to restore its behavior exactly as it was when it was saved. When loading a model, you need to understand its stored signatures, which define the expected inputs and outputs, like a contract. Check the model's metadata to confirm that these specifications match how you plan to use it, whether for real-time predictions or batch jobs. Make sure the inputs and outputs align with your pre-processing and post-processing pipeline, so the data format and meaning stay consistent. For instance, a fraud detection model should still take the same transaction features and return risk scores in the same format to keep business rules valid. After you load a model, treat it as active, but always run quick checks before using it for important work. Test it with a few known inputs and compare the outputs to earlier results to confirm they are consistent. This might mean verifying that a reloaded image classifier still labels test images correctly, or that a recommendation system still gives the expected suggestions. These simple validations help catch problems like using the wrong model version or mismatched preprocessing, and prevent hidden drops in performance. Regular checking builds confidence that the model still behaves as it did when it was originally trained. Python code, loading saved models. This script demonstrates how to reload machine learning models and verify that their predictions are correct. It focuses on the process of loading a previously saved model and checking that it still behaves as expected. By following along, you will learn the essentials of saved model reloading and validation. The line that begins with an exclamation mark is a shell command, not Python code. It tells the system to install TensorFlow version 2.20.0. Installing this specific version helps ensure that the later code runs correctly, since different TensorFlow versions can behave differently. This command is usually executed in a terminal or notebook environment before running the rest of the script. We begin by importing 3 key libraries for our work. The operating system library lets us interact with the file system, for example by creating folders and managing file paths. NumPy provides tools for numerical computing, especially for working with arrays and performing mathematical operations. TensorFlow is then imported as the main library we will use to build, load, and validate machine learning models. We set the random seed for both NumPy and TensorFlow to the same fixed value so that any random numbers or random operations they perform are repeatable. This means that things like neural network weight initialization will be consistent every time we run the code. Using fixed seeds makes our experiments reproducible, which is crucial for debugging and for fairly comparing model performance across different runs. This line displays the version of TensorFlow currently in use. It provides a quick check that your environment is using the expected version of the library. Confirming the version helps ensure compatibility with your code and makes debugging easier when something does not work as expected. The code first checks whether any physical GPUs are available through TensorFlow. If at least one GPU is found, it chooses the GPU, so computations can use its higher processing power. If no GPU is available, it falls back to using the CPU instead. This automatic selection helps the program make efficient use of whatever hardware is present. This code prints a message showing whether computations will run on a graphics processing unit or on a central processing unit. Knowing which device is being used helps you understand the hardware context for your TensorFlow operations. This information is important because it can influence both performance and compatibility of your computations. We are loading a small built-in dataset from TensorFlow's Keras module called MNIST, which contains images of handwritten digits commonly used for image processing tasks. This loading step returns separate training and testing sets, but here we only use the training portion. The training data is split into images and their corresponding digit labels. These images and labels will serve as the input data to train our model later in the script. To speed up training, the code uses only the first 2,000 samples from the training set. It converts the image pixel values to floating point numbers and normalizes them by dividing by 255, so they fall between 0 and 1, which is standard for neural network preprocessing. The corresponding labels are also selected and converted to integers, so they are ready to be used during training. To prepare image data for convolutional layers, we add an extra dimension to the array of training images. This new dimension, placed at the end, represents the channel information that convolutional neural networks expect. For grayscale images, this channel dimension has a size of 1, indicating a single intensity channel. This adjustment ensures the images have the correct shape for processing by the network. Before building the model, the code prints the shape of the training data to confirm that pre-processing worked correctly and the data is in the expected format. This check helps verify that the input dimensions match what the model needs. It is especially important after adding the channel dimension required by convolutional layers, so the model can be constructed and trained without shape mismatches. We build a simple convolutional neural network using a sequential model where layers are stacked in order. The network takes grayscale images of size 28 by 28 as input, then applies a convolutional layer with 8 filters of size 3 by 3 and a ReLU activation to capture features. The output is then flattened into a one-dimensional array and passed to a dense layer with 10 units. This final layer uses a softmax activation to produce class probabilities for the 10 categories in the dataset. The model is compiled using standard settings. It uses the Atom optimizer for efficient and adaptive training, and sparse categorical cross-entropy as the loss function, which is appropriate for multi-class classification with integer labels. In addition, accuracy is tracked as a performance metric. Together, these choices let us train the neural network effectively and monitor how well it is learning to classify the data. The model is trained using the fit method, which takes the small training dataset and its labels as input. It runs for one full pass over the data, known as one epoch. During training, it processes 64 samples at a time before updating its weights, which is the batch size. The training is set to run silently, with no progress messages printed. We take a small batch of data to quickly test the model's predictions. In this case, we use the first 5 samples from the reduced training set, including both the images and their labels. This limited subset makes it easier to check how well the model is performing without processing the entire dataset. It provides a simple, manageable way to verify that the prediction process is working as expected. The code uses the currently loaded model to generate predictions on a sample of the training data by calling its prediction function. It turns off extra output during this step, so the process runs quietly. This prediction step is important because it lets you check how well the model performs on the sample data before you save the model or try reloading it later. In this step, we turn the predicted probabilities into class labels by using a function that finds the position of the largest value in each set of probabilities. For every prediction, it selects the index of the highest probability, which represents the most likely class. This conversion from probabilities to class indices is essential because it allows us to directly compare the model's predicted classes with the true labels later on. The code displays the model's predicted labels next to the true labels for a small set of examples. This side-by-side view lets you quickly see where the model is correct or incorrect. By visually comparing predictions with actual labels, you get an immediate, intuitive sense of how well the model is performing on that subset of the data. We start by setting up a base directory called SavedModelsDemo, which will hold all the models we save. Using a directory creation function from the operating system tools, we make sure this folder exists, creating it only if it is not already there. This simple setup is important because it keeps our saved models organized and easy to find later in the workflow. This code defines where the model will be saved by creating a full file path that combines a base directory with a specific file name. It uses the operating system's path joining function to build this path correctly. The result is a location where the model is stored in the saved model format, so it can be easily loaded again later. This code saves the entire model to disk using the saved model format, so it can be loaded again later for inference or further training. Saving in this format preserves the model's architecture, learned weights, optimizer state, and any custom components. This makes it well suited for deploying models in production or sharing them with others while keeping everything needed to continue using or improving the model. The code defines where to save the model's weights by combining a base directory with a specific weight file name, creating a full file path. This path is used to store the weights separately from the rest of the model. Saving weights independently makes it possible to reload and manage them later without needing the entire model structure, giving more flexibility in how model components are handled. This code saves the model's weights to disk using TensorFlow's weight saving method. It stores only the learned parameters, not the full model architecture. This is useful when you want to reload the weights into another model that has the same structure. By doing this, you preserve the training progress without needing to save or reload the entire model definition. We reload a previously saved model by calling TensorFlow's loadModel function with the directory where the model was stored. This restores the full model architecture, its learned weights, and the optimizer state. As a result, the reloaded model behaves exactly as it did at the time it was saved. This is important to ensure that any new predictions match those produced by the original model. Next, we use the reloaded model to generate predictions on the sample data by passing the input through the model to obtain the predicted probabilities for each class. During this step, the detailed output is turned off so that no extra information is printed. This keeps the prediction process quiet and lets us focus only on the final results. The code takes the predicted probabilities from the reloaded model and turns them into class labels. It does this by using a function from the numerical library that finds the position of the highest probability for each sample. That position or index corresponds to the predicted class. In this way, each input image is assigned the class with the greatest predicted probability. The code prints the predictions made by the reloaded model, so we can compare them with the original predictions. By checking whether these predicted class indices match, we can see if the model behaves the same after being saved and loaded again. This comparison helps confirm that the reloading process has preserved the model's integrity and performance. We verify that the reloaded model behaves the same as the original by checking whether their prediction outputs match exactly. To do this, we compare the two arrays of predictions using a function that tests if all corresponding elements are equal. If the function returns true, it means every prediction is identical, and the reloaded model is fully consistent with the original model. This code checks whether the predictions from the reloaded full model are identical to the original predictions. It relies on a previously computed true or false value that indicates if the two sets of predictions match. The program then prints a message that reports this result, converting the true or false value into readable text. This simple check helps confirm that the model was reloaded correctly and still behaves as expected. To load the saved weights, we first rebuild the same model architecture using a sequential model in Keras. We define an input layer that matches the MNIST image size of 28 by 28 pixels with a single channel. Then we add a two-dimensional convolutional layer with 8 filters, a kernel size of 3, and a ReLU activation to extract nonlinear features. The output of this layer is flattened into a one-dimensional vector, which is passed to a final dense layer with 10 units and a softmax activation to produce class probabilities for the 10 MNIST digits. By recreating this exact structure, we ensure the saved weights can be loaded correctly. We compile the model so it is ready to load the saved weights and continue training or evaluation. In this step, we choose the Atom optimizer, which is commonly used because it trains neural networks efficiently. We set the loss function to sparse categorical cross-entropy, which is appropriate for multi-class classification problems. We also track accuracy as the main metric to measure how well the model performs during training and testing. In this step, the previously saved weights are loaded into the model architecture that was rebuilt earlier. This is important because it lets the model reuse the parameters it learned during training instead of starting over. By restoring these weights, the model can immediately make predictions or run evaluations as if it had just been trained. This approach maintains consistency with past results and saves significant time and computation. Next, we test the reloaded model that contains only the saved weights by using it to make predictions on the sampled data. We call the prediction function on this weights-only model and turn off any extra output so the process runs quietly. This step verifies that the model, after loading just the weights, still produces predictions that match those of the original trained model. The code uses a function that finds the position of the highest predicted probability for each sample, and this position is treated as the predicted class. In other words, it selects the class with the largest probability for each input image. This step is essential because it turns probability outputs into concrete class labels. These labels can then be directly compared with the true labels or with predictions from other models. The code verifies that a model reload using only its saved weights behaves the same as the original model. It does this by comparing the two sets of predictions with a function that checks whether the arrays are exactly equal. If the predictions match, it confirms that loading the saved weights successfully preserves the model's behavior. The code prints a message that checks whether the predictions from the model reloaded using only the saved weights are the same as the original predictions. It reports this as a simple true or false value. This serves as a final verification step to confirm that reloading the model from weights alone is reliable and preserves its prediction behavior. This script shows how to save, reload, and validate a TensorFlow model using the saved model format. It first trains a simple convolutional neural network on part of the MNIST dataset, then saves both the complete model and its weights.
This script reloads the full saved model,
Makes predictions on a small sample, and confirms that these predictions match those from the original model. It also rebuilds the same model architecture, loads only the saved weights, and verifies that its predictions are identical as well. This demonstrates that both full model saving and weights-only saving provide consistent and reliable model persistence and retrieval. Deterministic model predictions. When you reload a saved model, its predictions should be deterministic, meaning the same input and settings always produce the same output. This consistency is essential for debugging, satisfying regulatory requirements, and maintaining stakeholder trust. In sensitive areas like medical imaging, inconsistent results for the same scan make decisions harder and less reliable. Deterministic behavior lets you compare results over time and across systems, so any differences can be traced to deliberate changes rather than random variation. Ensuring this stability confirms that the saved model truly matches the one you originally trained and evaluated. To get deterministic predictions from a trained model, you need to control sources of randomness and verify that the reloaded model behaves as expected. While training uses randomness for tasks like weight initialization and dropout, inference should be stable once the model is exported. To confirm this, run the reloaded model on a fixed set of inputs and compare its outputs to a saved baseline. If the predictions match within an acceptable range, you can be confident that the model parameters and any pre-processing steps are consistent in the new environment. Some models behave non-deterministically during inference, for example when using Monte Carlo dropout or data augmentation, which can hurt prediction consistency in production. To handle this, it is useful to maintain two configurations, a deterministic one for production decisions and a stochastic one for research and analysis. When you reload a model, make sure it is set to deterministic mode with randomness disabled or tightly controlled. Clearly document these settings so predictions can be repeated and the model's behavior remains reliable and explainable over time. Python code deterministic model predictions. This script demonstrates how to get deterministic predictions in TensorFlow. It trains a model, saves it, reloads it, and then compares the outputs before and after saving. By confirming that the predictions match, you can validate that the serving model behaves in a stable and consistent way. The commented line recommends installing TensorFlow version 2.20.0 to keep the environment consistent. Using a fixed version helps ensure that machine learning models behave deterministically. It also prevents unexpected issues that might occur if newer versions of the library introduce changes. In short, specifying the version improves compatibility and reliability across different setups. We begin by importing 3 key libraries to set up our work environment. The operating system library lets us interact with the file system, such as managing folders and checking for files. NumPy provides tools for efficient numerical computations and working with arrays. TensorFlow gives us the framework to build and train machine learning models. Together, these imports prepare us to handle data, manage files, and create neural networks effectively. This code prints the version of TensorFlow currently in use. Knowing the exact version helps you check that the correct library is installed for your project. It is important for compatibility with other tools, for reproducing results, and for debugging issues that may depend on a specific TensorFlow release. To make our results repeatable, we set a global random seed so the code produces the same output every time it runs. We choose a specific seed value and apply it to the random number generator in NumPy. We then use the same seed value for TensorFlow's random number generator. By controlling randomness in both libraries, we ensure that any operations involving randomness behave consistently across different runs. The code first checks whether any physical GPUs are available using TensorFlow's device listing. If it finds at least one GPU, it selects the first GPU as the device to run computations. If no GPU is detected, it falls back to using the first CPU instead. It then prints which device is being used so the user knows whether the program is running on a GPU or on a CPU, since this can affect performance. We create a small, fully predictable dataset by first choosing 64 samples and generating evenly spaced input values between -1 and 1, arranged as a column. We then set the noise to all zeros so that no randomness is introduced. The output values are computed by multiplying each input by 3 and adding 0.5, with the zero noise leaving these values unchanged. Because there is no randomness at any step, this dataset is deterministic and will be exactly the same every time we generate it. The code first checks that the input data array has the correct shape, meaning the expected number of samples along one dimension. It then confirms that the output data array has the same number of samples, ensuring it lines up properly with the input. These checks verify that both input and output data are structured consistently, which is essential for accurate model training. By enforcing these conditions, the assertions help prevent shape mismatches that could cause errors during training or evaluation. We begin by setting the device context, so the model runs on the preferred hardware, such as a GPU, when available. Then we build a neural network with Keras, using a simple sequential structure, adding layers one after another. The model takes input data with a single feature, passes it through a dense layer with 8 neurons and a ReLU activation to introduce nonlinearity, and then through a final dense layer with 1 neuron. This last layer produces a single continuous output, making the model suitable for regression tasks. The model is set up for training using the Atom Optimizer, a common and efficient method for updating neural network weights. It uses mean squared error as the loss function, which measures the average squared difference between predicted and actual values and is well suited for regression tasks. Together, this optimizer and loss function define how the model learns from data and how its performance is evaluated during training. The model is trained using a fit procedure that takes input and target data and runs for 30 epochs, meaning it passes through the entire dataset 30 times. It uses a batch size of 16, so it updates its weights after processing 16 samples at a time. The training is run in silent mode, with no progress messages printed. The data is not shuffled between epochs, so it is always fed to the model in the same order, which helps keep the training behavior deterministic. We create a small, fixed test batch as a NumPy array with 3 values, -0.5, 0, and +0.5, and set its data type to 32-bit floating point. This batch gives us a consistent set of inputs for checking the model's predictions. We then assert that the array has a shape of 3 by 1 to confirm it matches the model's expected input dimensions. This check helps maintain consistency and prevents shape-related errors during prediction. The code uses the model's prediction function on a predefined test dataset to generate outputs from the test inputs. It turns off extra logging during this step, so the predictions are produced quietly. These predictions are recorded before the model is saved or reloaded, creating a baseline. Later, this baseline can be used to check that the model's behavior remains consistent and deterministic after any saving and loading operations. We first define a directory called deterministic model export to store our model files. We then check whether this directory already exists on the file system, and if it does not, we create it. The directory creation uses an option that avoids errors if the directory is already present. This setup ensures the model can be saved safely without running into file system problems. This code saves the entire model using the saved model format. It first builds the save location by combining the export directory with a file named fullmodel.keras. The model is then written to this path so that its architecture, learned weights, and training configuration are all preserved. This allows the model to be reliably loaded later for further training, evaluation, or deployment. The code creates a file path for saving the model's weights by combining the export directory with a specific weights file name. It then uses TensorFlow's SaveWeights function to store only the current model's weight values at that location. Saving just the weights separately from the full model makes it possible to reuse or analyze them without needing the entire model definition. This is important when you want to reload the same weights into a model with the same architecture to ensure consistent and reproducible results. The code loads a previously saved TensorFlow model from disk to check that it behaves the same after saving and reloading. By restoring the model from the given location, it brings back the exact architecture and learned weights from training. This makes it possible to compare predictions made before and after saving to confirm that the model's behavior is deterministic and unchanged by the save and load process. We begin by checking the input shape of the reloaded model to make sure it matches what we expect. Specifically, we look at the shape of its first input tensor and confirm that the second dimension is equal to 1. This tells us the model is configured to accept single feature inputs, just like the original model. Verifying this shape is essential to ensure the reloaded model is compatible with the data it will receive and to avoid errors during prediction. We now use the model that was saved and reloaded from disk to generate predictions on the test data. The prediction step runs silently, with no extra output, because the verbosity setting is turned off. This process is important because it lets us check that the reloaded model produces the same results as the original one. If the predictions match, it confirms that saving and loading did not change the model's behavior. To compare predictions, the code first finds the largest absolute difference between the baseline predictions and those from the reloaded model, which shows the maximum deviation between them. It then uses a numerical check to see if all predictions are close to each other within a small allowed error. If this check passes, it confirms that the predictions remain consistent and reliable after reloading, demonstrating that the model behaves deterministically. The code first prints the baseline model predictions in a simplified form so you can see the initial outputs. It then prints the predictions from the reloaded model in the same way, allowing a direct comparison. Next, it computes the largest absolute difference between the two sets of predictions to measure how closely they agree. Finally, it checks whether this difference stays within a small tolerance and reports whether the predictions can be considered equivalent, confirming that the model behaves deterministically after being saved and reloaded. We first choose whether to run on a graphics processor or a central processor, depending on what is available, so all operations use that device. Then, we create a Keras sequential model, which is a simple feed-forward neural network. It takes a single input feature, passes it through a dense layer with 8 neurons using a ReLU activation to add nonlinearity, and then through a final dense layer with 1 neuron. This last layer produces the single output needed for the regression task. The model is first set up for training or evaluation by choosing the atom optimization method and mean squared error as the loss function, which together define how its weights are updated and how performance is measured. After this compilation step, previously saved weights are loaded into the model. This restores the model's learned parameters from an earlier training run so it can make predictions consistent with the original trained version. We run predictions on the test data again, using the same model architecture after reloading the saved weights. This step checks that the model behaves consistently and deterministically, meaning it produces the same outputs as before. By comparing these new predictions with those from the original model, we confirm that the weights were loaded correctly and that the model's performance remains stable. We verify that the model's predictions from its weights match the baseline predictions by using a numerical comparison that checks each value with a very small allowed difference. If every pair of predictions is within this tiny tolerance, the function reports that they are effectively the same. We then print the predictions from the weights, rounding each value to 4 decimal places to make them easier to read. Finally, we print whether these predictions match the baseline, turning the true or false result into a clear, human-readable message. This script shows how to achieve deterministic behavior in TensorFlow model predictions. It fixes the random seed, trains a simple neural network on a linear dataset, and records its predictions on a small test set. The model is then saved, reloaded, and used to make predictions again, which are checked to match the original results within a small tolerance. The script also saves the model's weights, loads them into a new model with the same architecture, and confirms that this new model produces the same predictions. Overall, it demonstrates that model predictions remain stable and reproducible across saving, loading, and weight transfer operations. Handling missing dependencies. When you reload a saved model, it depends on having the same software environment it was created with, including the versions of TensorFlow, Keras, Python, and any custom layers or other custom objects. If these dependencies are missing or use different versions, the model may fail to load or behave differently in subtle ways. For example, a model that relies on a custom normalization layer will not load correctly if that layer's module is not installed or is incompatible. Matching the serving environment to the model's original setup is essential for reliable and consistent predictions. To manage missing dependencies when reloading models, focus on creating reproducible environments and clearly documenting all requirements. Record the exact versions of TensorFlow, Keras, and other libraries, as well as any custom objects needed at load time. When moving to a different system, use virtual environments or containers to recreate the original setup and install all required packages. Treat custom components, such as metrics stored in separate files, as essential dependencies and package them with the model to avoid incorrect behavior after reloading. Even if a model loads without errors, mismatched software dependencies can cause subtle prediction changes that only appear during careful validation. For instance, using a different version of an image pre-processing library in production can shift a computer vision model's outputs enough to reduce accuracy. To guard against this, run the same test inputs through both the original and the reloaded models and compare their predictions. If you see differences, investigate and align any pre-processing steps or libraries. This validation helps ensure the model behaves consistently in critical real-world uses such as medical diagnostics or credit scoring. In this lecture, you learned to export TensorFlow 2.20.0 models using the saved model format with appropriate signatures. Use Keras model.save and save weights APIs to manage checkpoints and full model exports. And verify that saved models can be reloaded and produce consistent predictions. In the next lecture, Lecture B, we will go over serving and APIs. Thank you for your attention. See you all in the next lecture.